So in the last video, I promised you guys that you're about to learn something that is maybe the most powerful thing you've learned in your scientific careers. And there's a reason why I believe that, okay? What you're about to learn are the three kinematic equations, or sometimes called the equations of motion. And what they say is that if you know some initial conditions, like the initial velocity, the acceleration of an object, you can find things in the future, like what will be the position of the object in the future and what will be the velocity of an object in the future, okay? So basically what you're about to learn is a crystal ball. You guys are going to become fortune tellers. You guys are going to be able to see the future, okay? That's why I think this is really powerful. It's almost like magic, okay? This is why we are able to put satellites in orbit. These three equations are why we are allowed to send probes that will eventually hit Pluto at some point and be able to take pictures of Pluto. It's very, very powerful stuff, and I'm about to share it with you right now, okay? So the three kinematic equations, if you go to the slide that says the kinematic equations, they take a form that is often used in books, but I like to simplify that form a little bit, and I'm going to share that with you right now, okay? So the first kinematic equation I like to write as V2, final velocity, the second velocity equals the initial velocity, right, the first velocity, plus the acceleration times time, all right? Second is V2 squared, final velocity squared, equals initial velocity squared, plus 2 times the acceleration times the distance traveled by the object, okay? And lastly, distance equals the initial velocity times time plus 1/2 AT squared, okay? So these are the three kinematic equations, and with these you could predict the future of any object's motion as long as you know the acceleration. Now, I should say one caveat, and that is that these equations only work when acceleration is constant, okay? So keep that in mind. How do we actually approach these for these like fortune teller or future reading problems, okay? Well, I'm about to tell you right now. There's a three-step process. If you guys could go to the next step or slide. It's 3 steps to solving every kinematics problem, okay? If you follow this 3-step process, you can't go wrong, okay? This is designed to get you the right answer every time. So here we go. The first step is always to do what I call making a laundry list, okay? And a laundry list is simply, we have 5 variables in these 3 equations, so you make a list of those 5 variables so that you can fill them in and know exactly what you have, okay? So don't take a shortcut. Do this always from the beginning. I've been doing these problems for over 20 years, and it's crazy that I can even say that, but I still make a laundry list every time I start a kinematics problem. So you should too. Okay, so first, V1, V2, A, D, T. These are all my variables, okay? So that's the first thing you do. You make a laundry list. Second thing you do is you use that list, right? Depending on what you have here, you use that list to pick which of the 3 kinematic equations you want to use, all right? And third, you simply solve for the variable in the equation that you're looking for, okay? Now, all of this sounds very abstract until we actually button down and do a problem. So we're going to do that. I have always been fascinated by really tall buildings, okay? Currently, the tallest building in the world is the Burj Khalifa, okay? It is 800 meters tall. That means, 8/10 of a kilometer into the sky, right? Mind-blowing to me. I've never seen it, and someday I hope to. For those of you who don't know that currently in Saudi Arabia, it's being outdone with a building that's planned on being a kilometer tall, reaching a kilometer into the sky. But I've always been fascinated with the question of, if I'm standing on the very top of this 800 meter tall building and I drop a gumball or something like that, right? How fast will it be going at the bottom? And will that speed compare to like a speeding bullet, okay? Fascinating question, at least for me. So how do we solve this? How can we use kinematics to solve that question, okay? Well, that's what we're about to do. We start with step 1, the laundry list. We ask ourselves, if we're about to drop that gumball, what are the 5 variables that we have? Okay, well here, I'm releasing this gumball from rest, right? And then it's accelerating. So my initial velocity should be 0 meters per second, okay? And my final velocity, when it hits the ground, that's the variable I'm looking for, right? Since I'm looking for that variable, I just put a question mark right there, all right? This question mark reminds me that's what I'm looking for, okay? What is the acceleration? Well, we know that acceleration is 9.8 meters per second squared on Earth, okay, in free fall, when things are in free fall. So normally, I would have to put a negative sign there, but I'm only dealing with one direction, right? I'm going down, so I can call down positive and everything's fine. So for the sake of this problem, I'm going to make that that simplification, okay? D, which is the distance, how far is that object traveling, right? Well, if it's falling from the top up to the bottom of an 800-meter building, that's going to be 800 meters. Again, because you're going down, technically that should be negative, but I'm going to call down the positive direction, okay? Just because I'm allowed to do that. And T, do we know how long it was in there? How long that journey was to the bottom? By the way, I'm just going to draw this here. This is the Burj Khalifa. Here's my gumball. And here it is falling to the ground, okay? Do I know the time? I don't. I don't know how long this guy was in the air, right? So if I don't know it and I'm not solving for it, I usually put an X, right? Or the poop emoji. It's the crap. We don't really need it, okay? All right. So step 1 of the 3-step process is down. We have our laundry list, okay? All right, so advance the slide to step 2, use laundry list to pick your equation. Guys, there's only one equation over here that has the 4 variables that we have and need over here. What do we have and need? We have V1, we need V2, we have A, we have D, right? So which of these equations has V1, V2, A, and D? 2, 1. Ding, 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 ding. It's the second equation, right? So we know that we're going to want to use V2 squared equals V1 squared plus 2AD, right? Okay, last step, the 3-step process, substitute and solve for the win. Okay, V2, that's what we're looking for. We're gonna leave that as our variable, okay? V1 is 0, so that's just 0 squared, right? Plus 2 times A is 9.8, and D is 800. Okay, so this obviously is 0. That's nothing. So then 2 times 9.8 times 800. I have an answer there. That is 15,680. Okay, I take the square root of both sides. I get V2 equals 125 meters per second. Okay, this would be the speed of that gumball when it hits the ground. All right. Now, I would like you, after this video, to do a little Google search or ask Siri, whatever you're more comfortable with, and find out what is the speed of a typical bullet and see if that is anything like that speed, okay? So could this be lethal, or is this just gonna be kind of like an uncomfortable clunk on the head, okay? It's an interesting question. Is it safe to drop a gumball? Now, whatever answer you get, I do wanna pose the question, is this totally accurate? Okay, there's probably many of you as we were doing this problem that's like, but did Scott think about that thing called, I don't know, air resistance or drag force? And the question is, very good, very good. I did not factor that into this problem. The truth is that we live on Earth and we have an atmosphere and we can breathe, which is great, right? However, that means that makes physics a little bit harder because that drag is going to slow this down a little bit and you're not going to have quite that high of a velocity. For now, in this course, we are going to pretend there is no air resistance, there is no atmosphere, right? Just to kind of understand the physics and be able to solve problems like this. But in the future, when we get to energy, we will start to include drag forces, all right? So for now, that is our answer. And you assume everything is free of friction, everything is free of drag, unless I tell you otherwise, okay? All right, in the next few videos, we will be doing some work examples to keep practicing this so that you can do kinematics in your sleep.